Good morning. My name is Chris Petersen, and I'm a hardware systems technologist at Meta. Today, I will be talking a little bit about memory requirements for AI workloads at Meta and some of the challenges and solutions that we're working through. AI workloads are used at scale across many applications and services and drive a portion of our infrastructure, both in terms of hardware and software. At a high level, we see the AI workloads fall into two big categories. Ranking and recommendation, for example, those models used to make video suggestions in terms of what might be interesting to a particular user, and content understanding. So these are, for example, computer vision models that do things like face recognition in pictures. We categorize them this way as they each have a unique set of characteristics that we would like to understand and design towards. These models will run both in data centers, at the edge, and even on the devices themselves. But for this talk, we'll focus on those that run within the data center. The core challenge we have to work through for AI workloads is the rate at which they scale. The two charts here help to demonstrate this point. The plot on the left shows the rate of scaling of a range of AI workloads over time in terms of the compute requirements of these workloads. The y-axis here is petaflops per second days and is a measurement of computational intensity. The x-axis here is in terms of time. Note that the y-axis is logarithmic, and we see linear scaling, and thus there's actually exponential growth. Here, we can also see that content understanding models are the most computationally intensive. On the right, we use the same approach, but in this case, we're tracking the number of parameters per model, which correlates closely with the size of the model and the resulting memory capacity. It is also loosely correlated with memory bandwidth. Here we can see that the recommendation models, for example, DLRM or Deep Learning Recommendation Model, are the ones pushing capacity requirements. The challenge here is really the rate of scaling of these models, which is much faster than the underlying server hardware technologies. That means we have to come up with other intelligent ways to help us scale. So let's dig a bit deeper into the recommendation models specifically. These models are the ones that are pushing both memory capacity and memory bandwidth requirements. There are several observations we can make here. First, we have the dense portions of the model, which are the most compute intensive. Second, we have the sparse portions of the models, which really stress the memory. When we talk about embedding tables, as I may do so in the future here, these are the implementation of the sparse portions of these models. Essentially, these are lookup tables. DLRM is a class of workloads. There are a variety of differences between the specific models themselves within this class, but they're essentially the same from a characteristics perspective, and we expect that to continue for the foreseeable future. We'll focus on this class of models for this presentation today. Let's unpack this even further and look at the memory requirements more closely. The two charts here show the bandwidth and the latency requirements. The x-axis is the memory capacity, and the y-axis is the bandwidth and the latency for top and bottom charts, respectively. For the top chart, the point highlighted by the red number 1 here, there's a considerable portion of the model that requires quite a lot of memory bandwidth, which generally resides in the accelerator memory. Most commonly, that ends up being HBM or high bandwidth memory. But as we go further down to point number 2 here, we see that there's actually a considerable chunk of the capacity that does not require as much memory bandwidth. It is equal to or less than the memory bandwidth requirement for main memory, for example, from DDR5 DIMMs, and gets close to what a storage device can operate at. This is a good sign, as this is a characteristic we can potentially take advantage of, and we'll talk about a bit more in the coming slides. But it's not just bandwidth that matters. Latency is very important also. The main takeaway from the latency chart, which is number 3, is that the latency band here is fairly narrow, which means that most of the accesses require fairly low latency. The application is tolerant of slightly higher latency than main memory, but it's definitely lower than what most storage class devices can actually provide. So what are the key takeaways here? Given the fact that there's a fairly large memory portion of the model that requires fairly low bandwidth, a tier of memory beyond HBM and DDR5 memory can be implemented. The latency requirement of this tier can be a bit higher than main memory, but the semantics and the latency profile does need to be fairly similar. For example, TLC NAND flash does not meet these requirements, and it is therefore not really a candidate for this memory tier. The other point is that we're primarily shooting to get a lot of memory capacity, and we're able to trade off some of the performance to be able to get there. Persistent memory technology or storage class memory technologies would be excellent candidates for this type of tier. Of course, we still need the HBM and the main memory tiers, but we're talking about an additional tier here beyond those to help us cope with the memory capacity scaling challenge that I alluded to earlier. So how does this fit within the end-to-end system? The primary way that we track the impact of building new systems is by looking at perf per watt and perf per dollar at the system level. Our goal is to be able to deliver what the applications need in terms of performance, for example, bandwidth and latency, but try to do it with the lowest possible power consumption and cost as possible. To realize these gains, we can apply a few different approaches, and we'll cover those in the next few slides. The examples we will cover are published in a white paper we have listed here at the top, so you can review them in more detail offline. The paper is focused on using NVMe SSDs as the potential memory tier, as these were broadly available at the time. As I mentioned, generally NAND flash will not be sufficient, but we can apply the same methodology that we explored here using things like storage class memory SSDs. Here we're showing that we can cache different embedding tables at different memory levels, with the hottest being stored in accelerator memory, the next level in main memory, and then the least access tables are stored on the SSDs. As we're talking about the inference portion of AI workloads, latency is a critical factor, and we need to be able to quickly access small chunks of data. This results in very high small block I/O access rates to the SSDs, which has resulted in us in implementing further Linux kernel optimizations, such as those around the IOU ring. There are, of course, quite a few additional optimizations that we can make here. For example, we can control the placement of the tables based on their size, their access rates, and the locality of these accesses. That gives us quite a degree of freedom to optimize algorithms to control the placement much more precisely and potentially tune it for different workloads as well. In summary, when we looked at this approach for two main reasons. First, in the near future, we will come to the point that these models are so large that we can no longer serve them if we don't solve this challenge. Secondly, even if we had enough main memory to serve these models, it would not meet our perf per watt requirements. And so we want to leverage these model characteristics to help build more efficient systems. Now let's take a look at a couple of scenarios that help us illustrate some of the power benefits that could be gained with this tiered memory approach. In this first scenario, we took one of the production recommendation models and tried to serve it using a simpler server design. The baseline system here is a typical 2-socket server, which we used as it provided a larger aggregate memory footprint that could accommodate this specific 143 gigabyte model. This system can handle about 240 queries per second, or QPS. The alternative system we looked at was a single socket machine that had a memory footprint that was smaller than the model size, but to accommodate the model, we added some storage class memory to the server to help us accommodate the entire model. And this storage class memory acts as this extra tier that I mentioned earlier. As we also need to hit a specific latency target for the queries that hit this model on both of these machines, on the simple server, we had to reduce the queries per second so that we could end up hitting these latency targets. That resulted in us having to reduce the QPS by roughly half. We then had to double the number of hosts to be able to serve the total amount of traffic that we have to be able to support. However, in aggregate, the simpler system was less than half of the power consumption of the baseline system, or about 40% of the power consumption. The net result, as we aggregate this across all of the systems involved, was that we came out ahead as we saved approximately 20% of the total power consumption across all of the servers. The second scenario took a slightly different approach, as we started with a different model. It's still a large model, 150 gigabytes in this case, but it also requires a lot more compute, as it contained a lot more dense elements. Since it's denser, it relied more on the accelerators to help us serve the queries. The accelerators themselves don't have enough capacity to serve the entire model. So in the baseline case, what we have to do is to scale out to other machines to help provide that additional capacity. In other words, we have to spread the model across more machines to keep more of the model capacity in the accelerator memory. We considered two potential alternatives to this. The first option was that we used NAND flash SSDs, but we didn't implement the scale out. In other words, the entire model was served from a single machine, but we had to really underutilize the NAND flash to be able to hit the latency requirements, which had a significant impact on the QPS that we could serve from this machine. Now, unfortunately, this actually made the total power consumption worse, so ultimately not a desirable option. The second option takes a similar approach in that we're not scaling out, but replaces the NAND flash SSD with a storage class memory SSD, which was capable of supporting much higher IOPS and also at a much lower latency. And as a result, we were able to match the target QPS for that baseline system, and we're able to load it onto a single machine. This avoided the scaling out effect of the baseline case and the additional power that comes with that, which ultimately results in approximately a 5% aggregate savings in terms of power. In addition to the power savings, however, we're also able to improve the aggregate operational complexity with this option, as we don't have to scale out across multiple machines and therefore it's much simpler to manage and load balance all of these machines. Let's circle back now to the original challenge, which was that we need to be able to scale our servers as AI workloads scale, and we need to be able to do so efficiently. By taking advantage of the model characteristics, we can apply a memory tiering approach. So if we take the typical storage pyramid, we can now start to see where things fit in as we start to add layers to the traditional gap between DRAM and NAND SSDs. We believe that these new layers are best served from CXL attached devices and are referred to here on this slide as bandwidth memory and capacity memory. For context, CXL, or Compute Express Link, is a new coherent interconnect built on top of PCI Express that provides cache line sized reads and writes to memory devices with a standardized approach. We now have a way to attach heterogeneous memory to a system to provide these new memory tiers, and we could take advantage of the capacity versus performance trade-offs that I talked through earlier. This particular AI use case that we covered today falls squarely into the capacity memory tier, as ultimately we need to be able to get as much capacity per machine as possible. So to wrap up, AI models are growing faster than the underlying memory technology, so we need to find new ways to continue to scale. Our work shows that additional memory tiers beyond main memory can help us address these scaling challenges. For example, the tiers that I mentioned earlier, this capacity memory tier. And we're able to trade off performance to help us gain additional capacity as well as additional TCO benefits at the same time. Finally, we believe that CXL and CXL attached memory devices are a viable solution to help us provide these new memory tiers and scale further into the future. Thank you for listening today, and we look forward to continuing to collaborate with the industry